Now I will present our SHREC 6-degree object pose estimation. It's a joint work of the following authors from 2 research groups. There are several reasons to organize this SHREC. Firstly, even though more and more algorithms aiming to estimate the object pose have been proposed, it's unclear how well these methods perform. This is because new approaches are usually compared with only few competitors on a particular dataset. Secondly, available 3D datasets that are used to estimate object poses have limited viewpoints and low resolution. On the other hand, collecting and labeling real-world data is a tedious and labor-intensive process. Last but not least, the object pose estimation has many applications, including visual navigation, robotic grasping, and virtual reality. Therefore, benchmarks are required to further enrich and boost the development of pose estimation research. The pose estimation has several challenges. Firstly, there are a variety of objects in the real world. They have different sizes and textures. It's hard to estimate the pose, especially for textureless or reflect objects, such as the milk box and the cup in these figures. Secondly, changing light conditions as shown in these figures may lead to the failure of the pose estimation. This is because in such conditions, it's hard to extract reliable features. Without enough features, it's hard to estimate the object pose. Lastly, pose estimation methods have poor performance for objects with heavy occlusion, as shown in these figures. Considering all these issues, we organize this benchmark. The goal of our benchmark is to investigate how different pose estimation approaches perform in terms of various object properties, such as sizes, shapes, textures, and occlusion. The dataset we provide has 8 objects which cover a variety of object properties you can see in this figure. Our training dataset is a synthesized one. It is generated by image-based rendering. Image-based rendering performs 3D warping that project pixels in the reference image to the world coordinate and then project the world points to new positions in another image plane to get a new image. Our testing dataset combines real captured and synthesized images for testing approaches. For each frame, we provide the following data: the object pose, color image, depth image, segmentation mask, 2D bounding box, 3D point cloud, and calibration information for each image. We use 4 metrics to evaluate the performance of pose estimation approaches. They are average distance metric, average closest point distance, area under the accuracy threshold curve, and reprojection error. Here we list the 3 methods we will analyze. Our baseline method is dense filling. 6D object pose estimation by iterative dense theory is a two-stage process. The overview of this method is shown in the figure. Firstly, the target object is detected in the input color image using segmentation. After that, the color and the depth images are cropped based on the segmentation. The cropped color image is fed into a scene-based network, ResNet 18, to extract color features. The point cloud, converted by the depth map, is fed into a PointNet-based network to produce geometry features. Secondly, the color and depth features are concatenated to estimate the object pose by a pose predictor. Lastly, the predicted pose is refined by an iterative pose refinement network. The second method is the ASS3D, Adaptive Single-Shot 3D Object Pose Estimation. In this work, they exploit multimodal inputs using a lightweight theory. In the first stage, they use two ResNet 34 models to extract features. In the second stage, the extracted features are fused and flattened by an average pooling function. After that, the features are fed into a pose encoder, which directly regress a rotation and translation. The predicted pose is used for rendering the object and deriving its predicted silhouette. This allows using an additional supervision signal during training, which increases the overall performance of the model. The last method is graph theory, 6D object pose estimation with graph-based multi-feature theory. The overview of this method is shown in the figure. In the first stage, the RGBD images are cropped with a segmentation to get the target object. After that, the color features are extracted by a CN-based architecture, and the geometry features are extracted by a PointNet-based network, just like dense theory. In the second stage, the extracted features are fused by a graph attention network, which is introduced to exploit the fusion strategy between color and geometry features. The object pose and its corresponding confidence scores are predicted by the fused features, and the final pose is chosen based on the confidences. Here we list the evaluation results of the 4 rounds of these 3 methods. Table 1 and Table 2 shows the overall performance in terms of ADD, ADDS, and AOC. We can see that graph theory achieved the best performance. We present ablation studies to help better understand the functionality of different network architectures. The following figures show the successful pose rate in terms of ADD for 8 objects. From these figures, we can see that dense theory and graph theory that performs iterative pose refinement are able to further improve the accuracy of the object pose. The following figures show the successful pose rate in terms of reprojection errors. We can see that graph theory outperforms other approaches, which indicate that viewing mechanism, considering the relationship between color and geometry features, has a clear advantage over methods which ignore this relationship. Compared with dense viewing and graph viewing, ASS3D estimates the pose in a single-shot network. It runs much faster than the other approaches, as shown in the Table 3. Our conclusions include, firstly, data-driven methods are the current trend in 6D object pose estimation. Secondly, the approach, follow exploring color and depth features, performs best, outperforming pixel viewing-based method and the approach with multimodal supervision. Let's continue with the future work. For pose estimation approaches, our insights can be used for many purposes. For example, it might be helpful to develop some novel methods to obtain better features. These features are helpful to estimate poses of reflective or textureless objects. For the datasets, the synthesized datasets need to be expanded by adding more reflective objects, occlusion, and varying light conditions. We also plan to make the data generation process more user-friendly, so that users can generate their own datasets for their own purposes. Thank you.